right, be sure to check the description of the video. There should be chapters and timestamps if you just want to go ahead and fast forward to whatever test you're looking for in particular. Otherwise, hang out with me and we're going to go through all the different settings, explain what everything on your meter means, show you a bunch of different test examples. Hey folks, and welcome back to the test bench. Today we're going to be going over all of the different settings on your Kaiweets digital amp clamp. Now, Kaiweets is not a sponsor of the channel, but they are an affiliate, which means that they send me links and discount codes and stuff. So be sure to check out the description to get the latest Kaiweets discounts. So why don't you grab a snack, have a seat, and let's get into it. This is the Kaiweets KC604. It's an AC and DC amp clamp. So when you're looking for amp clamps, it's important to think about the current measurements that you're trying to make. Are you going to need DC amperage measurement capabilities? Not all amp clamps are rated for DC amperage measurements. And so if you got something like this, it's great because it's rated for both. If we look here on our meter, we can see that there's a solid line and a squiggly line. The squiggly line is supposed to represent a sine wave for AC, and the solid line is supposed to represent DC. So the current measurements are rated for both AC and DC. And then we can kind of get a sense that by the values they have listed here on the manually ranging section, that it is probably a 4,000 count meter, which ain't bad for an amp clamp. We have hold and non-contact voltage on the side, min and max. Ooh, I'm not too familiar with the Z. The zero function. That'll be really critical for making DC measurements. Typically doing DC amperage measurements, the meter likes to float around a lot more. It's a lot more susceptible to noise. You're also going to notice Hertz and LPF. LPF is just going to stand for low pass filter. If you're trying to measure things that are coming out of like a VFD, it stands for variable frequency drive, there's a lot of switching that takes place. Let's kind of dive into this. LPF, low pass filter. So let's just kind of break down what that would mean. It means the low frequencies are going to pass through, are going to be allowed to be processed in our signal. And I believe the cutoff is at 60 Hertz. And the manual actually does a great example. It's got a great little diagram here. As we start to enter frequencies that are above 60 Hertz, up to 1K Hertz, it's going to start to taper them off and then completely cut them out and leaving you with a clean sine wave. And why would you want this? Well, when you're working with things like VFDs or inverters, it's creating a synthetic sine wave, and there's a lot of switching that takes place. So your sine wave, if you were to look at it on a scope, it can look, squiggly like this, or it can look really blocky like this. And this makes it really hard for the amp clamp to get an accurate measurement because this is inducing a lot of noise on our signal. And ideally, it wants something like this, a nice smooth sine wave. So having a low pass filter function will help clear out and smooth out this blocky waveform, and it allows the meter to interpret it as a nice smooth sine wave. So a really cool feature if you're working with some fancier motors and stuff, if you're working HVAC or industrial controls, having a low pass filter can really help with accurate current measurements. And then I'm sure you're familiar, but if you're not, Hertz is just the measurement of how many times something oscillates within 1 second. Typically here in North America, our AC power oscillates at 60 Hertz. In the rest of the world, it's at 50 Hertz. So it's a really common frequency that we work with in AC power. Now, before we get into doing our measurements with the amp clamp, I also want to break down something that's really nice is that they have two sections here for in the amp clamp. This portion here is kind of like a manual ranging portion. And what the clamp is basically trying to say is it can measure up to 400 amps in this setting, or it can measure up to 40 amps in this setting. And you might be curious like, well, why would it do that? Especially if we're in the 400 amp setting, it'll still measure currents that are 40 amps and lower, no problem. I want you to think of it kind of like the resolution. It's kind of like if we think about a microscope, if you were to set up a microscope, you usually put your glass, back here, and everything down here is kind of blurry. And then as you dial in your microscope, things that are smaller and further away come into focus in greater detail. It's kind of the same thing here. We can use the 400 amp setting to get a general idea of how much current a motor or something is pulling. And then if we can see that it's below 40 amps of current, well, then we can go ahead and move to the 40 amp measurement, and then our decimal on the meter will move over, and that'll allow us to measure to the hundredths place. So it'll give us a lot more detail and accuracy within our measurement. A part of this too, if we cycle through the function AC, DC, let's go ahead and take a current measurement of a motor and break down what's going on. Okay, so our scenario is we've got a big AC motor and we want to measure the current for it because we want to see if something's failing, and we want to take an AC measurement with our clamp, AC current measurement. First obviously we'll put it to AC. Our meter looks nice and zeroed out. There's two different options that you're going to have. If you're working in like a control panel or a breaker panel or something like that, you're going to have access to the individual conductors. And it's just important to remember that you need to put your clamp around either the hot or the neutral of the circuit. They're both current carrying conductors, so either one will work. A mistake that you might make or have made in the past is trying to make a current measurement and simply putting the meter around both the hot and the neutral, and you'll get a 0. And we can go ahead and demonstrate that here. So even though obviously our motor is running and it's drawing a significant amount of current, our amp clamp is showing 0. What is going on here? The amp clamp is picking up the magnetic fields created by the flow of current. And the magnetic fields are opposing in the hot and in the neutral. And when they're swapping back and forth like that, the magnetic fields are continuously canceling each other out. And so the meter reads it as 0. So in order to capture the current, we're going to have to go through either the hot or the neutral, and then we should be able to make a measurement. Now, something that I'm going to do so I don't have to keep running this motor is there's this H button on the side of the meter here, and that's going to stand for hold. So I'm going to turn on the meter, wait for a measurement to appear on the clamp, and then I'll press the hold button, and then we can talk about what we're seeing. I'm still in the 400 amp AC setting. Let's try it. Okay, and it shows it that this motor is pulling 7 amps of current. So we have our two settings up here, 400 and 40. Well, 7 amps is well below 400 and even smaller than 40. So we can go ahead and dial it down to the 40 now that we know what kind of current range we're working in, and we can take our measurement again and it should be more accurate. Let's make sure that it's set to the AC current setting again. It does default to DC, so that's something to be mindful of as you're swapping back and forth your 40 and your 400 settings. Okay, and now that we're able to measure to the hundredths place, we're able to see that, okay, it's not just 7 amps, it's 7.06. And why might this be handy? Well, it's going to be handy for making smaller and smaller measurements. You'd be surprised how little current things actually draw. especially when you're working with like 240, 480, 120. You might be asking, well, I'm not in a situation where I have access to my loads like control panel or breaker panel or something like that. I can't access the individual hot and neutral. What should I do? And your first instinct might be like, well, I need to cut into the cable. And I wouldn't recommend that at all. They actually have something built just for this scenario. And that would be something like a line splitter. You can get these online or in big box stores. A line splitter will separate the hot and the neutral for you. And then in the case of this line splitter, it has a times 10 function. So both on the top and on the bottom, it's letting you know whatever measurement you take with this will be 10 times the current value. So before we use this and before we use this, we can kind of think, okay, I know this is a 7 amp load, but this is going to multiply it times 10. So it should be roughly a 70 amp current measurement that my meter pulls. I'll need to put this back to the 400 amp setting and make sure it's on my AC setting, and I can try this measurement again. Now, if you didn't know that and you defaulted to the 40 amp setting, all you would see is an OL when you go to make your measurement. And the OL is telling you that the measurement that you're making is out of limits. It's saying, hey, this is way too much current for me to recognize. You need to go to the next setting up. So I've got my amp clamp in my line splitter. I know that my line splitter has a 10 times magnification. If you're curious how it magnifies it times 10, it's a very simple principle of it takes the conductor and it wraps it around. So like this would be times 2 because my conductor loops through my clamp 2 times. 1, 2. And then if I do it a third time, now it's going 1, 2, 3. That would be times 3. So basically the conductor internal to the line splitter is looped around 10 times, and that's what gives us the 10 times 10 magnification. That's really handy information to know if you're trying to make really small measurements that are too small for the clamp to pick up accurately. You can make your own line splitter, basically separate your positive and your common, or your hot and your neutral. You can wrap one of the current carrying conductors around your clamp, and maybe you do it times 5. That'll give you a times 5 magnification, and then you divide it by 5, and that'll give you a nice, good, accurate reading. So now that we have times 10, we're in the 400 amp setting, AC. Let's go ahead and flip the switch. Look at how accurate that is. In our up to 40 amp setting, where we were able to read to the hundredths, we saw, what was it, 7.06. And in our times 10, if we times it by 10 and then divide it by 10, we get 7.08. So you can see that the magnifying by 10 and dividing by 10 can be just as accurate as having a much lower magnification setting on your meter. So that's something that you want to keep in mind if you want to get really, really accurate measurements. And that's why we're able to measure up to such a high amount of current, is the higher that we multiply to and then divide by, the more accurate we can get our numbers. So I always thought that was a pretty cool part of amp clamps. So that takes care of the AC. Let's go ahead and talk about DC, where it's going to be important to keep in mind our electron flow, because it will be directional measurements. Okay, great. So we've got this little motor here. It's a DC motor with the DC power supply to it. We have access to separate, power and common. You can see I just set it to the DC function. Now remember, it's going to be the same rule of thumb. Opposing magnetic fields, same thing with DC. If I turn on this motor and I have it wrapped both of my conductors, I'm not going to really get any kind of a good measurement. Let's try and re-zero this. Let's try that again. Output. Right. So we can see our motor is running. It's around both conductors, and it's saying, 20 milliamps with the current, which I know that to not be the case with this. And even as we load up the motor, we're not really seeing a change. It is going to be directional. So that's something that'll kind of throw you off if you're not familiar with doing DC amp clamps. And if you have your clamp oriented in the wrong direction, you're going to get a negative sign. So you'll still get a fine measurement. It'll just be negative. Let's take a look and see if we got it in the right orientation. Okay, so we see that negative sign popping up. We are actually getting a current measurement this time. So to flip my direction of my amp clamp, all I have to do is like that. Take our current measurement again, and this time we see we have a positive value, and it's a very small value. This is only like 420, 430 milliamps of DC current, and there might even be a range listed in the manual. For me, if it's ever less than like, 1 whole amp of current that I'm measuring, if I'm able to, I'll just go ahead and wrap it. So what we can do, we might even be able to do this in live time, right? So we have our measurement showing about 450 milliamps of current. Now I've got 2 ramps, so now it's double, triple, quadruple. So then if I wanted to, now that I have well over an amp worth of current, I have 1.72, I can divide that by 4, and that should be a much more accurate current measurement. All right, let's go into checking the voltage of an outlet. I would always recommend using a dedicated outlet tester. This one's even by Kaiweets, but it doesn't have to be by Kaiweets, it can be by anyone. And this one has some indicators here telling us if the wiring's correct, and it even displays the voltage. The LEDs are much brighter in real life. They don't pick up on the camera that well. What I can see on the LEDs here, I've got this LED and this one lit up. And if I look at my chart, it's telling me, hey, the hot and neutral are reversed. And it told me that information in such a quick amount of time that this is the way I'd always recommend it. However, you're not always going to be working, obviously with outlets that are going to be able to use just an off-the-shelf outlet tester. Sometimes you're going to have to measure outlets with your meter, and then you're going to have to discern, who's wired who, where's your hot, ground, and neutral. It's going to be especially tricky if you're missing your ground pin for whatever outlet you're working with. You're going to need a ground pin to be able to figure out which one is hot and which one's neutral safely with your meter. But I'll show you how to do that here. I've got it in volt AC setting. I've got a hot outlet here, and I can use my probes to open the outlet doors. And there we go. My screen turns amber, letting me know voltage is present. And then it gives me a value of 121.6 volts. It is true RMS. If you're not familiar with RMS, basically it's trying to say when it's measuring AC voltage or current, it's giving you a root mean square value. And that's because if we were to think about our AC waveform, it's not a static value like how you would have with DC. Like this would be 0 volts, this would be 12. With AC, it's constantly flipping from positive to negative, yet we have a static value on our meter. So with root mean square, it's just saying, hey, we're giving you basically the average value of this, because coming out of this outlet right now is closer to like 145 volts AC, peak voltage. Okay, but our mean voltage is going to be somewhere right around there. Okay, so I have voltage at my outlet. That's great. But what I just saw on my outlet tester, I know that these are reversed. How do I figure that out? Well, that's when your ground pin comes into play. We can remove one probe and go to ground and see what our potential is. Our potential is almost nothing. It's like 150 millivolts, right? It's just like ghost voltage on there. So that tells me that this right pin here is going to be my neutral. And in the US, for our wiring standards, that right pin should be the hot, and it's not. So I can put my other probe back in here, go back to my ground, and now I can see, oh, I've got 121 volts potential difference between my ground and this prong. So this prong must be my hot. I've got them swapped. So that's kind of how you would go about figuring that out. And then as far as DC measurements are concerned, I mean, compared to all the stuff we've just been doing, they're about the easiest that you can do. You just make them in parallel, red to positive, black to negative, and we get a value there. We can press H for hold. Look at that. And see how the flashlight is on this thing. Oh, this is the flashlight button. Okay, not terrible. I've seen a lot worse. That's actually pretty good. That'll get you enough to help you like navigate a panel for sure. Okay, and then we have Hertz and duty cycle. I know that we've already talked about Hertz. All right, so Hertz and duty cycle are two different things. So we want to keep that in mind when we're doing our measurements. Hertz is going to be how quickly something flips back and forth or turns on and off, right? They're going back and forth. And in 1 second, how many times does it do that? That's going to be Hertz or frequency. They can be interchangeable. And then duty cycle is always expressed as a percentage. And duty cycle is, for something like this, if we have like a pulsing square wave, if that pulsing square wave is on all the time, it's 100% output. If our duty cycle is like this, where it's these pulses and it's on about half the time and off about half the time, this is 0 volts and this is 5, this would be really easy, 50% duty cycle. And then if you have pulses that are much larger, it's on most of the time and off just a little bit of the time, well, then your duty cycle is probably about 80%. And so you can measure both of these with the Hertz and duty cycle section of your meter. It defaults to Hertz. And sometimes there's limitations on the Hertz on the voltages that you can measure Hertz. And then let's just flip over to duty cycle. And like this little meter here outputs a little square wave. And we should be able to measure both Hertz and duty cycle. This is saying that this is putting out 50% duty cycle. So our pulses are on half the time and off half the time. And then we can cycle to Hertz. And then it's saying it's doing this 47.64 times per second. So it gives us a lot of information about what waveforms are doing without having to get out of scope. So it's nice to have both those little functions. Let's see, this is gonna be for diodes, capacitance, continuity, and resistance. Man, this meter is packed with a lot of functions. I know they're an affiliate, but for the price, I don't know. I'm sure you probably did a lot of looking around before you settled on this one, or maybe you're considering this one. For the price, that's a lot of functions to fit into one meter. It's gonna default, it looks like, to resistance. So you can use resistance measurements not just to measure resistors, but you can do it for checking continuity for like an electrical load or circuit. You can see here like this light bulb says there's 1.2 ohms. So there's good continuity here. If I measured this light bulb and my measurement came back like that, OL, OL in this context means open loop. The electrons can't flow, the circuit is open, so I'd probably have like an open filament in my bulb. But we can just run through and look at resistive measurements. Something that we really want to pay attention to is going to be the units that show up next to the ohm symbol. So we can see there it's just a horseshoe, but if I measure another resistor, K is for 1,000. So this value 9.98, I would want to remember to times by 1,000. So the value, the actual value of this that the meter is saying is 9,998. For this one, we've got a 1 with an M. M is for mega, or think of millions. So this is saying, hey, this is 1,046,000 ohms. What it goes to next is continuity. Continuity is great for doing those quick checks. It emits a tone, the screen lights up, and that's just letting you know that electrons can flow through your circuit. You can also use it for discerning wires with terminals. That wire doesn't go there, but it goes there. Because oftentimes when we're working with a lot of wires, we can't always see them. They're usually tucked behind walls or dashes or whatever. Next function is going to be capacitance. I've got 2 different capacitors here that we can take a look at. One's for the homeowner, one's for the electronics hobbyist. This is an AC run capacitor. You always want to make sure that your capacitors are discharged. You can just short out the terminals. It's recommended to use like a 10K ohm resistor when doing that and not just a screwdriver, but it's a very low amount of capacitance in this. So for this capacitor, how we could do this is we've got our C. C is for common, put our common lead there, and then our red lead we can put to Herm, and we can see it's going to come back with 35 microfarads. That's what that funky looking U is that you've probably never seen before. And then we can also check to our fan, because this is 2 capacitors built into one, and it's showing 5 microfarads. So on the label here, it says, hey, there's one capacitor rated for 35 microfarads, and there's another capacitor rated for 5 microfarads. They both need to be within plus or minus 6%. And this capacitor, the reason why it's so big is it can handle up to 440 volts AC. Unlike this capacitor, which has a much, much more capacitance to it, but is rated for a way smaller value. And so something like this, we can just short out the leads for it really quick. It's got a negative side on this side. We can see that it is rated for 680 microfarads at 16 volts. Give it a second to charge up. And it comes in at 642 microfarads, about 640 microfarads. So this one, I believe, should be within plus or minus about 10% of its rated value, and it does. So the capacitance of these two is testing good. Next up, we have diode. I'll just do this really quick. So I've got a diode here. I've got this stripe of the diode on the right-hand side right now. I'll do this first test here like this, where my red lead is on the left and my black lead is on the right where the stripe is. And the value that we're seeing there is the amount of voltage drop across the diode. We typically want to see about between 500 and 800 millivolts of voltage drop in one direction. And then in the other direction, we want to see that OL, and that's telling us open loop, or basically that there's no backflow of the diode there. So there's that. Next up is thermocouple. Switch out our leads. We could do something like this. Thermocouple is really straightforward. It's just a really fancy temperature measurer. Black lead into COM, red lead into input. And then something I always like to do before I use my thermocouple to make a measurement is I'll grab the ends of it with my fingers and double check that, the temperature is going up to an appropriate amount. That tells me that my thermocouple leads are good and that it's working properly. So there's that, and then function for Celsius. Low Z. Low Z can be kind of confusing. Although if you work with a lot of AC circuits or like an AC signal noisy environment, low Z is about the handiest function that you can have for a meter. And I want to kind of touch on it because even in the instruction booklets or reading about it online, it can be really confusing. Low Z has nothing to do with the impedance level of the circuit that you're trying to measure. And I think that can be the really confusing part of this. You don't need to know anything about the impedance of the circuit that you're measuring to use the low impedance setting. The low impedance refers to the impedance of the meter itself. You're lowering the internal impedance of the meter. And what is this going to do? This is going to put a little bit of a load on an AC circuit and drop off inductive ghost voltage. And I will set up a demonstration. Okay, we're going to play a little game because that's what troubleshooting is at the end of the day, isn't it? I've got my meter set to just the standard AC volt setting. And here, let's say we're in a panel or some kind of box somewhere out in the field, and we're trying to troubleshoot a circuit because it's acting really funky. And we've got a hot and a neutral and a ground. If I measure between my neutral and my hot, what do I get? I get 15 volts AC, just about 15 or 16. If I measure between my hot and my ground, I get 147 volts AC. And if I measure between my neutral and my ground, I get 22 volts AC. If you were out in the field, you would be chasing your tail. You would be so confused with those measurements, you wouldn't even know where to start, right? As we can see, our neutral is not hooked up to anything at all, and there shouldn't be any voltage on it. But you can see it's coiled up next to my hot, which does have voltage on it. That's the great thing about AC is it's very inductive. It wants to put voltage on things just around it, but that also creates a lot of noise. We have this low impedance setting. It lowers the internal impedance of the meter and basically induces a small load on the circuits that we're testing. Very, very, very small load so that it's still safe. But what this is going to do is drop off any of that ghost inductive voltage that we have that's just floating around on dead circuits. Now we can retake our measurements. We can go from our hot to the neutral. Okay, we're showing like 400 millivolts. Okay, we're showing like basically a dead circuit. If I go from my hot to my ground, okay, I'm showing 147. So my hot seems to have some serious voltage on it. Now if I do from my ground to my neutral, there's just a couple little things floating on there. It's like 700 millivolts. So it's dropped off completely, where I think before we had like 22 volts. You could have thought that, oh, maybe there's a 24 volt like DC system that's like touching or something like that. The low Z setting is really great for dropping off ghost induced voltages, and it's going to really help streamline your troubleshooting if you're working in a very AC heavy environment, like an industrial environment around a lot of motors and control circuits, stuff like that. Helps drop everything off to make your troubleshooting easier. Anyways, that is the Kaiweets KC604. That's a lot of bang for your buck, I gotta say. So that was a good time. If you guys are learning this stuff, I've got a bunch of different shorts and everything like that to help break down a lot of different electrical components. I've got a bunch more Kaiweets meters on the show. I have a bunch more meters in general if you're out shopping for one or want to just learn more about your meter. So thanks for joining me, and I'll catch you on the next one.